Hi guys, this is Mrs. Gastler, and in this video we're going to talk about some special cases of uniform circular motion, and that is going to be about vertical circles. And so I have here some circles that I already drew. This, if you can't tell, is a hand. I'll label it there for you. That's a hand, and we're swirling something around in a circle. It's a vertical circle, so this is up and down, up, down, okay? And so we're going okay, with an object. When we're talking about vertical circles, really the only places that we usually care about are the very top and the very bottom of the circle, because some special things happen there. And when we're thinking about what's going on in this kind of circle, there's usually a string attached that we're swirling it around, and a string when it gets down here. Not that there's two things swirling at the same time, but that it's going around either clockwise or counterclockwise. Is usually how we describe that motion. And two things happen here. When we're getting up here, there are two things that are pulling this object down. Not only is gravity pulling on it, but there's also the tension from the string that is pulling on it. And one of those may be bigger than the other. I don't really know which one is bigger than the other, but I know that the gravitational force is going to be constant. And then when we get to the bottom, gravity is still pulling it down. Okay, well there, the gravity is the short one up there. But this time tension is going to be pulling it up, okay? And some special things have to happen in order to get this to take place. Actually, the tension here, I've drawn it the same, but it's not actually going to be the same because if this thing is going in a nice uniform circular motion, what's going to be constant the whole time is going to be that centripetal force. Is going to be constant. So let's see, these two added up is going to be about, I don't know, that long, which means these two added up also has to be about that long, which means this tension down here, we'll call this FT up, and we'll call this FT when it's down, which actually is a little confusing because they're pointing the opposite direction. This one actually wouldn't be that short. This one would have to be longer so that the centripetal force would actually be constant. Now, have you ever felt that before? When was the last time you whirled something around in a vertical circle? Try it. If you don't have any things that you can whirl around in a vertical circle at home, you can ask to do it in class. You can actually feel that, right? When it's down at the bottom, you have to pull a little harder, right? It's not quite so hard. In fact, you can kind of let go a little bit at top. In fact, there's a minimum speed that you can swirl this at where only gravity is providing the central force and there is no tension at the top. And then there is tension at the bottom and then no tension at the top, so that the only gravity is the centripetal force at the top. In fact, that's probably a question you're going to have to answer at some point in time. What is the minimum speed with which you can swirl this so that gravity is the only centripetal force at the top? In fact, I think that is the example that they give in the textbook. But the things still apply. So remember, we have that centripetal acceleration is v squared over r, and that centripetal force is mv squared over r. And so if you want the gravitational force to be the centripetal force at the top, then you just want mg to be mv squared over r. Which means that the masses cancel out, and so g equals v squared over r. So that minimum speed, all I have to do is solve for v, right? So v equals g times r square root of that. So this is the minimum speed, so that there is no tension at the top. If I go any faster, I'm going to need some tension to keep it coming down. If I go any slower, the string is actually going to be, or the object isn't going to be going fast enough to stay in the circle, and it's going to kind of come down a little bit. So if I were going to draw that, my path would actually go right, okay, which is not actually uniform circular motion. Gravity is going to be taking it out of the circle instead. So that's a fun question there, okay? In other situations, you're going to have to think about what's going on because sometimes, so this is like, instead of a string swirling around, what if this were like a dryer that is on its side, or one of those front opening washing machines swirling the clothes around to get the water. to come out. Okay, the water actually goes out this way, not straight out. When I have the close on the inside, okay, right there, the normal force is going to be providing the central force. So if this were my close, okay, then a normal force would be providing that central force. But at the top, gravity would also be providing that as well. So at the top, I would have Fg, okay. That looks confusing, sorry, but that's fine. Fg at the top is going to be pointing down also, and Fg at the bottom is still pointing down. Okay, that's what you have to include there. If I had something that was on the outside of the circle, or if it like a Ferris wheel or buckets or something like that, on, what do they call that? There's this one kind of, I can't think of what it's called, those things with the water, and you get the water and it turns for electricity. I can't think of what those things are called. Wow. Serious brain fart there. It's okay. You'll come up with it and tell me. Where the bucket of water is this way, then there's a normal force that's supporting it upward, and so gravitation is down. So you just have to think about the orientation of things and which way those centripetal forces, well, the centripetal force is always going to be toward the center, but all the forces that are acting on it are going to be pointing in different directions. So it's going to be really important to think about the forces that are involved and which way they're pointing. So some tips. What forces are there? Which way are they pointing? What makes up the net force? And how does that relate to the centripetal force? How does that relate to the centripetal force? And then once you have all of that information, then you can start plugging in these kinds of things up here with the central acceleration and the mass, and thinking about whether or not this mass cancels out. A lot of times the mass does cancel out. Sometimes it doesn't. And what are you looking for? The other question is, what are you looking for? What are you looking for? Because sometimes you're not looking for the central force. Sometimes you're looking for one piece of information that is inside one of the forces, and that is, you're just setting up these equations like we did up here to be able to find one piece of information that was inside one of them. And so using those formulas to be able to answer the questions, that is definitely something that you need to be able to do. So there's some practice problems for you to work through. Let me know if you have any questions. Thanks for watching.